This tutorial will cover the CLSE 202 Aspen simulation project. We'll start by looking at the Rankine cycle. So when you open Aspen, it'll take you to the specifications under the Components tab in the Properties section. We're going to input Steam as our component ID for this Rankine cycle. Then we'll go to Methods, and for our base method, we'll put Peng Robinson. So then we'll go to the Simulation tab, and for the Rankine cycle, we have 2 heat exchangers, and then a pump and a compressor. So we're going to horizontally rotate this top heat exchanger so that the streams will flow in a circle, and then we'll click Material and connect all of the streams to the units to form the cycle. And then I'm going to go ahead and rename the units and the streams as well, just for organization. And here is what all of the named streams and units look like. Next, we will click on the compressor, and under specifications, we will start to input our data. So we're given that the temperature of the compressor is 100 degrees Celsius, and the pressure we can get from a steam table to be 0.101 megapascals, which is atmospheric. Then we'll go to the pump, and for model we can leave this as pump, and then for discharge pressure we will put that as 3 megapascals, which was given. And then for the pump efficiency, we'll assume that to be 1. Next, we'll go to the boiler, and the temperature of the boiler is given as 600 degrees Celsius and the pressure as 3 megapascals. Then we will go to the turbine. For model, we'll change this from compressor to turbine, and the type will select isentropic. And then for the discharge pressure, we will input 0.101 megapascals, which again was found from a steam table, and this is atmospheric pressure. And then we'll assume the isentropic efficiency to be 1. So next we will input our information for our streams, and because it is a cycle, all of the streams have the same information, so we can just input it to one of them. So I chose the low pressure water, and the temperature for this stream is 100 degrees Celsius, and the pressure is 0.101 megapascals. And then for the composition, we'll change that to mass flow, and because there's only one component, we can put 1 here, and Aspen will assume that to be 1 kilogram per hour. Then we can go ahead and run our simulation, and this will take a second. So this came up with a warning message that basically says that there are no inlet or outlet streams, but because it is a cycle, this shouldn't affect the results. So lastly, we can go back to the main flowchart and click on the boiler to see the results of this unit. We'll have to change the units to kilojoules per hour, and we can see the value there. And we can also go and look at the work produced by the turbine, which is given in kilowatts. And these values were very similar to the hand-calculated values, which indicates that the simulation is fairly accurate. Next, we'll look at the vapor compression cycle simulation. So we'll start in the same place with the component specifications, but here we'll put the chemical formula into the alias, and then HFC134A into the component ID as our refrigerant. And then under methods, for base method, we'll put the Peng Robinson. So now we'll start building the flowchart, and for the refrigeration cycle, we have 2 heat exchangers, as well as a throttle valve and a compressor. And again, we will rotate this top heat exchanger horizontally so that the streams flow in a circle, and then click Material and connect all of the streams. And again, I'm going to rename the blocks. And here's the flowchart completed. So first we can start by clicking on the condenser unit and inputting the specification. So we're given that the condenser runs at 55 degrees Celsius, and then using a Moliere diagram we can find that the pressure is 1.5 megapascals. And because we know that the outlet of the compressor is a saturated liquid, we can change the valid phases to liquid only. Next, we'll look at the valve, and we can leave the calculation type as pressure changer, and the outlet pressure is 0.35 megapascals, which is also found from the Moliere diagram. And the valid phases we can leave as vapor and liquid. Next, we will look at the boiler. So we can input the temperature as 5 degrees Celsius, which was given, and initially I input 0.35 megapascals as the pressure, which was found on the Moliere diagram, but this did not work. You have to input the vapor fraction in as 1 because we know that it is a saturated vapor. So then we'll look at the compressor. And this is isentropic for the type. We'll leave it as compressor for the model. And the discharge pressure is 1.5 megapascals, which again was found from the Moliere diagram. And for the isentropic efficiency, we can assume that to be 1. And then we'll have to go to convergence and put vapor liquid as the valid phases. Lastly, we will input the stream specifications, and again, since this is a cycle, we can just input the specifications for one of the streams, so I selected the high pressure liquid. The temperature we know is 55 degrees Celsius, and the pressure is 1.5 megapascals. And then we can change the composition to the mass flow, and again, just input 1 as the value here because there's only one component. So then we can run our simulation. An error message does come up, but that was fixed once I changed the specifications of the boiler stream. It was coming up that the compressor feed stream was below the dew point. And the results were incorrect because of this, but here are the corrected results once I fixed the evaporator specifications. And those were for the evaporator, and then the compressor. Again, this warning message is from the incorrect specifications, but here are the corrected values, and both of these corrected values are very similar to the hand-calculated values. So that is how you make a Rankine cycle and a refrigeration cycle in Aspen Plus. I hope this tutorial was helpful.